All right, I think we shall start. So this is XCI team here from Keysight. We're going to talk about running system-level experimentation and doing so efficiently. I'm Alex Bortek from Product Management, and with me today we have Razvan Stan, who is a software development leader, and Thomas Amelin, software architect. Also, I have Dan Michalescu, who is participating in a virtual session from Romania. So I'm going to cover first two topics, which is what kind of goals you might have today for running system-level experimentation, and what kind of problems you might face in doing so. And Razvan going to follow up with a demo of the way we can, we think you can increase efficiency of system experimentation. And then Thomas going to cover our efforts to describe system experiments using open models and APIs. So on the left-hand side here, I have a red exponential curve that represents the growing demand for processing power that is coming from the content we generate. And the other curves, they demonstrate how we grow processing capacity of compute clusters by scaling them out horizontally. So there are a couple of patterns here. The one which is demand always wins. And then our approach of overcoming that demand by employing new generations of compute is not working that well because the gain we get from the new generations of processors is diminishing. So the approach we're taking currently is to make this curve steeper by adding things like hardware acceleration, offloading more cycles from CPUs to DPUs, looking for, to optimize network topologies that interconnect nodes within the cluster, and so on. So these measures work better if you understand what kind of application you are designing your cluster for. Another way to say that if you do is application-tailored design of your compute cluster, you get better results. Now, if you have multiple applications you have to go after, that means you essentially need to experiment more and more because there are so many designs you have to pursue. And so that's why we are talking about system experimentation. Let's look at the machine learning example doing model training job. So the contributors to the job completion time are how much time it takes to ingest the data into our processing cluster, the time it takes to compute it every cycle, and then, very important, how much time it takes for all the nodes in the cluster to exchange the data before the next computing cycle can start. So we want to focus our attention right now in this communication part. And if you want to improve the communication time, there are multiple contributors to things like tail latency that impacts that the most, which is TCP stack you have in the kernel or specialized communication library you're using. Might be NIC, driver for the NIC, or DPU, data center fabric, its topology, how the nodes of the cluster are connected to the topology, and so on. So these are the areas you would have to experiment with. And if you approach that in a brute force manner, so to say, by running a real job, making your adjustments, and then rerunning the job again. So there are several problems here. First of all, the tooling you need to run a real job is quite complicated. So there is a steep learning curve here. Then, because it's a real job, you have to actually use quite expensive and powerful servers in your experimentation setup, and also interconnect them to something that resembles a real production network. So you end up with quite expensive clusters. And if you cannot afford that and you try to run experiments in production, then you have probably some uncontrollable variations that are making your experimentation a little bit less predictable. So we thought there should be a better way to approach experimentation in this area and build a few tools to address these problems. So remember, we are talking about experimentation and improving the communication time. So we don't really need to compute, if you think about it. Instead, what if you can just reproduce the communication pattern that happens between the nodes in the cluster and focus on improving that in that area. The second one is, what if you can reproduce the data center fabric by emulating it instead of building it out? So you would have to spend less money on switches. You maybe just end up with using a single switch. And then also you can iterate faster by looking at the different topologies, different settings within those topologies, placing nodes in different places, and you don't have to spend time on rewiring everything. And finally, introducing chaos is very important, but you want to do it in a controllable fashion, so you need some tooling for that as well. At the end, we want to make sure that when you set up such an experiment, you can describe it in a way that you can share with other teams so that the experiment can be reproduced, maybe another team, maybe by a vendor, and so on. So that's where we want to focus on the standardizing the models and the API to describe the experiment. So we're going to show you the demo of those tools today. And those tools are under the umbrella of Keysight Dice. And they are, the first part is the one that emulates workflows, runs on servers. It's a specialized software. The servers are connected to a OCP spec white box switch, for which we created a special purpose fabric emulation network operating system. That NOS has capabilities for network impairment as well. And in our demo, we're going to be using Jupyter Notebook and the open models that we are building to describe the experiment to derive it from the Jupyter Notebook. So I'll pass it over to Razvan, who's going to be playing a role of a network performance, of a performance modeling engineer in this challenge.
Hello. Hey, everyone. Hey, good morning. All right, so what you see here is actually a Jupyter Notebook where we orchestrated the experiment. And for this part of the presentation, I'm going to play the role of a performance modeling engineer that wants to experiment with the communication pattern of a machine learning job and play with different network settings, fabric settings, workload settings, and see how that affects the job completion time of that pattern. So that below is the pattern. So this is the data exchange graph, the pattern that I'm going to be running, actually the middle part in the blue rectangle with two all reduced stages. And I'm going to run this over 16 servers. It's the hardware that Alex showed you before. 16 servers hooked up in a mini data center with TORs and pods, so two pods interconnected with a spine switch. And a little bit of flare there, it's an impairment that I'm going to talk about. On the side, we created like a small script to loop through different settings. Like, for example, what if I try different fabric settings like buffer size? And what if I apply some different impairment settings on the links up to the spine and put different loads and see how, if I create congestion at that point, how does that affect the job completion time when I run all that workload over the servers. And the last loop is the workload settings, like, for example, try different MTUs and different congestion algorithms, and run everything, save the results, and then load and do some data mining. All right, so that's the script. And then back to the data exchange. So what it's doing actually, right? So you have 16 servers. It's doing two exchanges of all-to-all meshes. Every endpoint pair is doing about 1 gigabyte of data per flow, so 240 per stage and 3.8 terabits for the whole job. So that's the amount of data is being transferred between these servers in the mini data center. All right, so assume I ran all this yesterday, and we can run about 2,500 experiments in a day, collected like 5 gigabytes of data, and we're going to pick a couple of results and zoom in to take a closer look to the results. All right. So for the first result that we're going to look is from the amount of data and the combinations, like I said, fabric load and MTU and congestion algorithm. So we're going to pick when the spines were loaded 25% with some aggressor traffic. So all the data, we plotted here. I just chose the heat map. I thought it's a good way to visualize the job completion time. Breakdown by on the vertical by congestion algorithm, and on the horizontal by other parameters like MTU or initial congestion window. Lighter is better. So just by looking at the heat map, you can see that this DCTCP is performing better than all the other combinations. And for example, if there's no load on the spines, in this case, BBR is performing better than all the other congestion algorithms and the combinations. So by having the ability to run multiple experiments and gather a lot of data over the course of a day, you have different ways to look at the data and zoom in and maybe find a pattern and take it from there. So for the next part of the demo, I'm picking one of the cells, which is the combination of BBR with MTU 4000 and a few other things, and we're going to rerun that particular combination of parameters. So three experiments here. One is just rerunning, and you can see that that's the workload that we're running. And overall, it provides a job completion time for the whole thing to finish. But then the whole job consists in different endpoints exchanging data. So which one of the endpoint pairs contributed to the job completion time being so much, right? So we can drill down into the results. For the second part, the fabric being all emulated, you have the liberty. The whole cabling is virtual. So you have the liberty to move things around, to change the fabric. And you have this kind of flexibility. So we can swap the servers between the TORs, for example. Or maybe even put them all in one pod and see if that produces better job completion time. So all right, so with that in mind, the first experiment, the first rerun, so just rerunning that combination of parameters and rerunning the data, and then we're going to switch to a viewer for the network emulation part we created for this demo. So the experiment is running, and now this is the top emulated fabric viewer. You're going to see on the side is the configuration as JSON, and on the left side, you see the actual emulated fabric with the 2 pods interconnected with a spine, and you have 3 TORs per pod. The 2 TORs in the middle are used for aggressor traffic to put the load on the spines and create congestion. And you see it's giving live feedback with, you see green activity and red means loss. So it's very vibrant and live, and you can use it for debugging, for example, because it gives you that kind of status. On the side, right, so at the bottom you see the 16 servers we have connected, actually the setup that Alex was showing you before. And then on the side, it's the configuration. And imagine instead of going box by box and configuring and interconnecting this, you have a simple configuration with how many spines, how many pods, how many racks per pod, and just, boom, creates the whole emulated fabric for you. You don't need to learn a NOS, very simple JSON configuration. So imagine how easy it would be to just use it to play with different fabric settings. So the run itself finished, so we have a little script there to plot the results and look at the results. Running, so this is a CDF of the flow completion time. You see 3 series here. The 3 series are for different flows that finished within a TOR and within a pod, and flows that cross the spine, right, between pods. And you can see 2 things. One is long tail latency, and another one is flow completion time actually depends on the distance, which is not good. But this is what happens when you have, you have a lot of data and you can represent it and you can investigate, right? Another way to look at the data is do the same heat map. that we did for the job completion time. So this time is for the flow completion time. So having 16 servers, I just put them like in a matrix like this on horizontal and vertical. So the intersection of a row and a column represents the flow completion time when these two nodes exchange data. So again, lighter is better. And if you look, immediately something stands out. Every flow that initiated and terminated in server N2 actually took longer. So if one node, right, the overall training is distributed, and it depends on all these servers exchanging data. So if one node is slower than everyone else, the overall job completion time will suffer, right? And in this case, you see we have a bigger, we have a big contributor to the job completion time. And for the next part, because the cabling is virtual, we're going to take these 4 servers, and we're going to swap them with the servers in the Thor number, in the pod number 2, and see if the problem moves with the server or stays with the Thor, if it's a fabric configuration issue or if it's something particularly misconfigured on that server. Right, so this is the swapping the servers. The fabric stays the same, but you're working from home. You do all this configuration remotely. You don't even have to go to the lab to change a cable. So this is cool. All right, so starting the demo. And the experiment. So this is just zooming in on the fabric to show that the servers now are swapped. So on the first servers, right, the N0 to N3, I don't know if you can see the label. So they are now part of the second pod. So we switch the servers just by changing a configuration piece. And again, running is fast. Right, it's replacing the communication of that machine training learning job. And you can see here by plotting the heat map, actually the problem moved with the servers. So indeed, there's something particular happening with that server. So it gives us enough data to go and investigate further. What's going on? Why are they not configured consistently? And that's it for the demo. All right. Thomas, you want to take it from here?
Thank you, Razvan. Oh. There we go. So we saw how you can run many experiments and how you can analyze them. But we want to do more than that. We don't want to stop just at building a tool or 2 tools and that's that. What if you want to collaborate with others? What if you want to enhance use cases, cover new things? You want to have your users run the same experiments that you're running. Or maybe you want to run on a different platform, maybe in a live network. So let's take a look. How do we make that happen? Let's unite, engineers unite, and let's make it open, and let's make it easy. So traditionally, APIs have been kind of heavy and cumbersome and difficult to use at times. So we want to propose something different here. And that is the Open API document, which is the single source of truth that will define declarative models, and that's key, declarative models and lean APIs. So as you can see, what does it really mean, right? So for example, the bulk of the information will be in the models. So you can, for example, define your data flow as Razvan and Alex were showing earlier, like a scatter-gather or the different data patterns. You would define that in your model. That's where the experiment is defined. And then as a result, the API is very thin, very easy to use. It's basically apply this configuration, run this experiment. Now, we don't want to build a monolith. We don't want to build everything into one. So what we're proposing is to separate it into different verticals, right? So if maybe you only want to use the fabric emulation part, you're free to do so. Optionally use the chaos engineering aspects of this. But maybe you just want to run the data flow traffic generation, right? So maybe you have 2 DPUs that you want to compare in your servers and your setup, and you have already switches in the lab that are wired up, and just by taking only the data flow portion, you can run only that experiment. Now, coming back to the demo that Razvan was showing us earlier, this is just to give you an idea, right, what you would see and to put more color behind what I mean by declarative models. Right? So on the left, you see some excerpts of the example configurations that we ran. You have the host components where you define the names you saw on the heat map, the N1 through N16. So that's what would go there with their addresses, for example. A separate section would define the data flows, which nodes are involved, what are the operations. Let's say you have a all reduce, or the different steps that could, for example, make up ML training. And then other parts that would go in there is Razvan was experimenting with different TCP congestion algorithms. That's where that would go. And then the next section is the fabric configuration. So it's in here it's very simple, like how many spines, how many pods, what makes up a pod, what is the ECMP configuration, those kinds of things. And then the last part there you see is the chaos configuration. So for example, introduce a percentage packet loss on a particular link, for example, to emulate real-world conditions. And then, these different portions get applied to the different pieces of our demo setup. The data flow configurations go to the server where our data flow emulation software is running. And then on the OCP white box switch, that's where the fabric configuration is going, and that's where you then have your spines, your TORs, and so on running on the ASIC, or being configured on the ASIC, on the switch. Now, this slide is key, right? Why are we here? So we talked about OpenAPI and the model and all that. So there's a rich infrastructure that generates different SDKs, like there will be a Python SDK, there's a Go SDK, you can write it like an API, you can choose to take that model configuration that we were looking at just earlier, and you can use it in JSON and YAML, you can even use protobuf text if you want. There's different transports, and all that is auto-generated and driven by that OpenAPI document. And then on the right side, we see there can be different implementations of these models. So for example, there could be one implementation that has a simulation backend, something like NS3, and you want to run your experiments up front. Maybe your data scientists want to do that. You can. So you define your experiments in the models, execute it on the simulation backend, you get your flow completion time and your job completion time. Or maybe like in what Razvan was demoing earlier, you run it on real ASIC with our emulation platform, or maybe there is a backend that takes the experiment into a data center, into maybe a test pod or something. And the key here then is that the same experiment will work on any of these platforms. So thank you. There's many people that made this possible, and you can read their names here. And there's also a couple presentations that we want to call out. In particular, also last year at the Virtual Summit, we had the Bringing the F16 Network into the Lab presentation that inspired our Fabric emulation. Thank you. And one more thing. We'll be at the booth later. You can find us here. We take Q&A also, but we'll also be at the booth if you want to come talk to us. We'll be happy to talk to you. So the call to action. Let's build good open models, bring them, and we would like to bring them under the OCP umbrella. If you want to engage with us, please come. There's the GitHub URL listed here, or search for Open Network Experiments 1x. And if you have use cases that you want to contribute, if you want to talk about the models, if you would like to share experiment results with us, we'll be happy to hear from you. And then, like I said, as we get traction, we would like to bring it to the OCP. Thank you very much, and we take questions.
Okay.
All right.
Thank you.
Very good.
Thank you for your
Thank
time.
you.
Yeah. Thank you.